All right, welcome to the notes on 3-1. We've gone back in time. We're going back to the parts of Chapter 3 that we need, and we're going to merge that with some parts of Chapter 4, and it's going to be a great time. Anywho, solving systems using tables and graphs, this should be pretty easy for us because, one, it's very calculator heavy, and two, a lot of this stuff is Algebra 1 stuff that we're good at, or hopefully that we remember some of, so it makes it a little bit easier. So solving a linear system using a graph or a table. System of equations is just a set of two or more equations. Okay, so a solution of a system, in this case we're going to talk about lines. Okay, a linear system is linear equations. So a solution of that system is a set of values for the variables that make everything true. All right, we can do this with a graph very simply, where we graph both lines and we see where they intersect. It's really just that easy. When you have where you think the intersection is, you can plug that back in, and when you plug -4 and -2 into each equation, they should come up as true equations. Okay, so it's just a very easy way to see where the two lines intersect is the solution of that equation, so no problem there. We can also use the table feature in our calculator. I'm not as big of a fan of this because I think there's a lot of guessing involved. Specifically right here where it says adjust the x and y values. We can talk more about that in class, and I'll show you what I mean. But if you put this into your table function in your calculator, or in a TI, you would just put y equals and then hit table. Well, first though, you do have to solve it for y, and then you'll see where the y values are the same. So 1x and we get 2 y's. That is the solution. So here's what I'd like you to do. If you want to graph it in your graphing calculator, you can do that too, and I can show you how to find that. Go ahead and pause the video right here and see if you can go through and either, whatever way you want, graph these two lines and come up with the solution to that equation. Go ahead and pause the video now. To that system, sorry. Pause. All right, so you've unpaused. You can see the first thing I did is that I changed them both so that they were set equal to y. I solved for y on both so that they were in slope-intercept form. You can do that and then graph them by hand if you want. I went ahead and just put them in my calculator. I went to menu, graph. I entered them both in, one here, one there. I click draw. I get this. I can see the intersection, so I don't need to change my view window. I hit F5, intersection, and the answer is 2, -1. It is really that easy. Okay, so 2, -1 is our answer here. No problem. Using a table to solve a problem. The diagrams show the birth, lengths, and growth rates of two species of sharks. If the growth rates stay the same, at what age would a spiny dogfish and a Greenland shark be the same length? These are things like I ask myself all the time. Such great real-world applications. If you're wondering, shark length. We should change the curriculum so that we cover this stuff during Shark Week, but then that would mean that we were in summer school, and that means that things didn't go well. Okay, so here's the equations for each. And we have the x right here, and we can see that it's going on and on and on, and we use the table to solve the problem, and when the x values have matching y's, then we have our answer. This could not be easier. How long will each shark be when it's 25 years old? How would you find that out? You would plug the 25 in for the x, right? So you're going to do that. And then explain why growth rates for these sharks may not continue indefinitely. See if you can explain that. Go ahead and pause the video right now. Get the length of each shark at 25. And then also give me some words in the form of a sentence as to why the growth rates might not continue indefinitely. All right, so here's what I got. I got the spiny dogfish at about 59.5 centimeters, and the Greenland shark at 55 3/4 centimeters. And then for part B, I just put at some point the shark stops growing, right? Like it has a max length. If we figure out some sort of growth rate equation for humans, and then you live to be 120, you're not going to be 14 feet tall. That's not how it works. So at some point, it's going to stop. All right. That's it. This stuff's pretty easy. Linear regression. Okay, we've done quadratic regression. Now we're going to go back in time and look at linear regression a little bit. Very easy stuff for us. Two sets of data. That's the only difference here. We're going to solve. We're going to use solving systems and combine it with our knowledge of linear regression. We're going to put this in our calculator. And so we're going to list 1 is all the same, list 2, and then list 3. And then we're going to use linear regression, and list 1 and list 2 are New York, list 1 and list 3 is Los Angeles. We graph the lines, we see where they intersect. Um, this stuff's easy peasy. We can do this stuff. Okay. So if you would please, if you could try to put in your data, get some answers here for number 3. When were the populations of these regions equal, and what was that population? So just what's the intersection of those two sets of data? Go ahead and do that now. So when I did it, I got that in the year 1990 they were about the same, and the population was about 1.1 million. This is some really like intensive calculator stuff. So if you aren't getting that, or you don't know how I got it, make sure you bring your calculator with you to class, and we'll walk through the exact steps to make sure everybody can do this. Okay. The last thing is that we need to be able to classify a system of two linear equations by the number of solutions. So we have a couple things, a consistent solution and an inconsistent solution. And then from a consistent, we have two options. It can be independent or dependent. So here's how it works. If we have intersecting lines, that is consistent because there's one solution, and it's independent because there's one solution. If we have coinciding lines, so they are the same line, that's consistent, but it's dependent because there are infinitely many solutions because the two equations are the same line. If we have parallel lines, there is no solution, and that is an inconsistent system. Okay, that's it. We just got to be able to classify them. So, classifying without graphing, well, what would you do? Well, the easiest thing to do is just to change them to slope-intercept form, and then look at them. Here, the slopes were the same, and the y-intercepts were different. So these are two parallel lines, so that system is inconsistent. If you could go ahead for me and get answers to 4A, B, and C, making sure that you understand these. This is a perfect way to set up, if you're taking notes, intersecting lines, coinciding lines, and parallel lines, and it tells you exactly what they are. So go ahead and get answers for 4A, 4B, and 4C. Pause the video now, please. All right, you've unpaused. Let's get some answers here. 4A, hopefully you got that this was inconsistent. Okay, inconsistent. For B, hopefully you said that was independent. And for C, hopefully you said that was dependent. All right, and that's it, guys. That's it for the notes. Hopefully this wasn't too bad. There are some calculator things here, so we have to make sure we know how to use our calculator. So bring them with you to class. I'll show you how to use them. It'll be great fun, and you'll wish you had a Casio. And yeah, that's it. See you next time. Bye.